Accredited webinar series. Let me start that again. Now we've got the recording going. So good afternoon, everyone, and welcome to the second in our three-part CIWEM CPD accredited webinar series. We're going to be looking at how we model the impacts of climate change on global flood risk. My name's Gavin Lewis, and I'm the Head of Engineering here at Fathom, and I'll be your host this afternoon. And I would like to thank CIWEM for their assistance and guidance in the development of this three-part CPD webinar series. I'm joined today by my colleagues, Dr. Natalie Lord, who is our Senior Climate Scientist, and Dr. Nan Zador, our Principal Hydrologist, and Tom Collins, who is our Lead Coastal Developer, and he'll be joining our question and answer session at the end of the presentation. So we'd really encourage you to ask us questions. And if you have any questions, please ensure you put them in the Q&A panel that you should be able to see on the screen in front of you in Zoom. So please use the Q&A panel and we will pick those up and review them and answer them at the end. Okay, as I mentioned, this is the second webinar in our CIWEM series. The first webinar we held back in December last year was an introduction to global scale flood modelling, in which our flood experts explored the methods, considerations and science behind global scale flood models. This first webinar can be found online, and the link to the webinar will be in your chat panel shortly. In this second webinar, we're going to discuss the processes by which climate change is transforming the behaviour of flooding, the use of climate models to anticipate future flood risk and some of the uncertainties in these types of models, how we move from a global climate change model down to a much more local scale flood hazard models, together with some project references and use cases of the flood hazard data across the engineering spectrum. Before we start, I'll give you a bit of background as to who we are at Fathom. Fathom was formed by two PhD students here at Bristol who were researching methods to build better flood models at global scales. And they set up this business to provide a much better understanding of flood risk globally. Consequentially, Fathom has developed a range of global flood maps in addition to high resolution flood maps for the UK, the US and Japan. But all these data sets cover both current and future flood risk scenarios. In addition to flood maps, we also do catastrophe and cat model loss models as a derivation from our flood maps. And we work across a range of market sectors, including insurance, financial services, government, NGOs, and of course, engineering and across the built environment. With our strong academic pedigree, we have continuously researched new methodologies for flood modelling, which are published in the world's leading academic journals. We're very transparent about our scientific research and methodologies, and all our papers are freely available on our website for you to go and download and review. And I'd really encourage you to do that. And they start off from our earliest papers on 2D flood modelling to one of our latest papers on the impact of climate and flooding across the UK. And these papers also include quite a few papers where we've co-authored with various different organisations on a range of flood-related topics. Before we dive into the technical section of today's webinar, I'd like to please answer this poll that we're going to have now on climate resilience. So whilst that poll's going on, I'd like to mention that our previous webinar is available on our website. If you go and search under events, I think you'll find it there. You're able to log in, register, log in, and view and download a link to the webinar. And I'll be talking about our next webinar a bit later on. So we've got some great responses there. Thank you for that. It's quite an interesting answers. Okay, I think that's probably enough now. Thank you very much for your responses to that. Very interesting, and we'll share those results in the emails we follow up with. Okay, so what I'd like to do now is introduce you to Dr. Nans Adar, who will be talking about climate change and transition to flood hazard. For some reason, let's move on. Okay, some reason, okay. Right, Nans, over to you.
Hello, everybody, and welcome. So today I'll be giving you an overview of how climate change is already transforming flood hazard. And then we'll discuss how we can predict future changes that are induced by climate change using models. Next slide, Gavin, please. So we'll be talking about pluvial, fluvial, and coastal flooding. And really a good starting point to understand what's going on is, as often, the water cycle, and specifically what's happening to the atmosphere. So humans are releasing large quantities of greenhouse gases into the atmosphere, and these gases trap heat. And this means that the atmosphere is warming up, as many of you will know. So the current level of warming is about 1.2 degrees Celsius above pre-industrial levels. And just to give some context, the Paris Agreement is trying to limit warming to 1.5 degrees Celsius. So a warmer atmosphere can hold more atmospheric moisture. And it is about 7% more per degree Celsius, and that's known as the Clausius-Clapeyron law. And the fact that the atmosphere can hold more moisture means that it can fuel larger rainfall events and generate larger flash floods. But what's really interesting is that even though we see larger river flood peaks in many locations around the world, there are many locations where we find that flood peaks are getting smaller. And we'll discuss why it's the case in this webinar. So this was pluvial and fluvial, and for coastal, a warmer world means warmer oceans. Warmer oceans are oceans that expand, and this causes sea level rise. A warmer world means also that there is more ice that is melting on land, melting quicker. So I'm talking here about ice in glaciers, in Antarctica and Greenland, and this is also contributing to sea level rise. And these two processes lead to more coastal flooding. So let's start by asking, how have things already changed over the last few decades? Because, I mean, climate change is not something that will happen in a distant future. It's happening now. And when we use records and look back a few decades, the impacts are very clear. So let's talk about them a little bit. Next slide, Kevin, please. So this is a good starting place because in this paper, they showed that climate change both increases and decreases European river floods. So they used about 50 years of data based on 2,370 stations across Europe. And they looked at changes in annual maximal flow at all these locations. And locations where they see larger flood peaks are in blue, and the ones with smaller flood peaks are in red. So they divided Europe in three regions. Region 1, northwestern Europe, where we are, where the UK is, experienced actually larger flood peaks over the last 5 decades. And this is because of an increase in rainfall and soil moisture, meaning that there is more water available to generate floods. But interestingly, if you look at region 2 and 3, the red, so in Southern Europe, they found that there is a decrease in rainfall and an increase in evaporation, meaning that there is less water available to generate floods. And if you look at Eastern Europe and also Scandinavia, there is a decreasing and earlier snow melt. So in a warmer world, the snowpack is thinner, and when it melts, the flood peaks are smaller. So there is really a combination of drivers that explain these changes in river flood peaks. So this analysis, just for Europe, has been repeated at the global scale. Next slide, Gavin. And this is what you're showing here, you're seeing here. So same analysis, they're looking at 70 years roughly, based on slightly more stations. What you see in the bottom plot is that the spatial distribution of the station is very uneven. And there are regions like Africa and Asia where we don't have many river gauges. So it's hard to know what's going on. But in regions where we know what's going on, we can compare changes in annual maxima precipitation at the top and flow at the bottom. What we see at the top is that in most of the location, there is an increase in the intensity of extreme rainfall events, right? It's many blue dots. But if you look at the bottom at extreme flow, you see that there are a lot of dark red dots indicating that flood peaks have become smaller. So if you focus just on Eastern Europe that we just talked about, you see that there is an increase in the intensity of extreme rainfall events, the blue dots, but this does not result in an increase in annual maximum flow. Actually, flood peaks are becoming smaller in Eastern Europe, right? So they can be very different responses of precipitation and flow to a change in climate. So because we don't have good data in many parts of the world, there is sometimes the temptation of using the Clausius-Clapeyron relationship to project changes under current and future climate. Next slide, please. And this paper here explored whether it's realistic or not to use Clausius-Clapeyron to predict changes worldwide. So here they did not look at trends, they looked at the change in extreme flow and precipitation at the top per degree Celsius of warming. And what you see when you compare these two maps, that rainfall and flow respond quite differently to a temperature increase. But what's really interesting, I find, is that if Clausius-Clapeyron was a good predictor everywhere for flow, extreme flow, and extreme rainfall, then these two maps would be red, they would be dark red, and definitely they're not. There are many regions where we don't see a change in extreme flow, and there are many regions where we see actually smaller flood peaks. So I think this paper is a good illustration of the limitations of using the Clausius-Clapeyron law to make predictions worldwide. Next slide, please. And so talking now about coastal flooding, the top map shows the change in tidal flood frequency. And you see that in many locations, the dots are red, which indicate an increase in the flood frequency, though there are a few locations where we see far less frequent flooding. What's important to keep in mind here is that a small increase in sea level can lead to large changes in return period. And this is illustrated by the plot in the lower left corner. And you see that in Hawaii, 11 centimeter change in sea level will turn a pretty extreme 1 in 50-year event into a very common 1 in 1-year event. So this is just to illustrate that what can be a change in sea level that can be perceived as a small change can actually have a really large impact on coastal flood risk. Next slide, please. And so far we've talked about changes that we have already observed, things that have already changed. Now let's talk about how we can use climate models to get a better sense of future changes in flood hazard. Next slide, please. Yeah. So the starting point for studies looking at anticipating future changes is typically a climate model. And these climate models come in two main flavors. We have general circulation models, often called also global climate models, GCMs. And these models are run at pretty coarse resolution and they cover the whole globe. Another type of model is called RCM, so it's a regional climate model, and it only covers a region of the globe, for instance, Europe. And these models are run at much higher resolution because the domain they have to cover is smaller, so it's affordable to run them at higher resolution, and typically their results are more reliable when it comes to extreme. So climate models can be used to look at changes in extreme rainfall. The simulation can be used to force hydrological models, and so we would use temperature and precipitation and radiation, wind to use as input of hydrological models, or they can use CARPOL with ocean model to look at changes in coastal water levels and flood hazard overall. So this is a framework that is typically used to look at changes in flash flooding, extreme river flows, and coastal water levels. Next slide. There are a few good practices that it's important to keep in mind, and probably the first element is that even the best model out there is not perfect. And it's really important to use an ensemble of models, an ensemble of climate models, an ensemble of hydrological models. And this is also how we estimate the uncertainties in the future changes. Another good practice is to pick the latest generation of models. So CMIP6 is the latest generation of climate models. The previous one was CMIP5. And whenever possible, and Nat will talk more about it, there are clear benefits of using high resolution climate model runs when possible. Even high resolution climate models show biases, so bias correction is often necessary before the simulation can be used to drive, for instance, a hydrological model. So there are different approaches to estimate future changes. We've already talked about a few of them. One can look at trends or at changes for global warming levels. And one can look at annual maxima or changes in return period. And over the next few slides, I'll give you a few examples of different approaches. So this is a study that basically used the most accessible approach to look at future changes in river flow and extreme river flows. So they're looking at trends over a period of 150 years, so going to the end of the 21st century, and they use the output of 11 CMIP6 models. So they use directly the river flow simulated by the GCMs. The GCMs were definitely not designed to simulate river flow, but river flow is part of the water cycle, and GCM simulate the water cycle. So it's one of the variables they simulate. What's important to keep in mind here is that the resolution of GCM is really coarse. We're talking 100+ kilometers. So there are significant uncertainties in this simulation, but that's an option if one tries to have a very general idea of what the changes are. The top panel shows the trend of annual maxima for precipitation, and you see that the map is blue. It indicates that in almost all the regions, all the locations, we're expecting an increase in the intensity of rainfall event. If you look at the bottom figure, we're looking at annual maximum flow, and as we've discussed already, the picture is more nuanced, and there are many regions where we're expecting smaller flood peaks. Next slide, please. Another approach, which is a little bit more involved, is to, instead of using directly the flow simulated by the GCMs, one can use the runoff and then use a routing model to simulate the flow. And using a routing model means that you can operate at finer resolution than the grid of a GCM. In this specific study, they look at changes between the current period and the last 30 years of the 21st century. And they're not looking at trends, they're looking at changes in the 1 in 100-year event. So the top row shows changes. When you see red, it means less frequent flooding. And what's really interesting in this specific study is that if you look at the two successive generations of models, CMIP5 and CMIP6, the two maps at the top look actually quite similar. So there's actually a really good consistency between these two generations of model simulations. The bottom row shows model agreement, and model agreement is high in regions that are shown in red or in dark blue. And you see that model agreement increased slightly, but there are still many regions where there's still pretty large disagreement on the sign of future changes in flood peak. So yeah, this is a persistent source of uncertainty when it comes to future climate and future changes in river flooding. Next slide, please. So another way to look at changes is to swap time for global warming levels. So this is just an example to illustrate what it's all about. We have two models, model 1 in blue and model 2 in orange. And you can see that's the temperature that they simulate, and you can see that they warm up at different rates. The model 1 warms up quicker than model 2. And so if you look at when they cross the 2-degree line, you see that for model 1, it's around 2060. And for model 2, it's not until 2083 or something like this. And so one way to approach climate change is to say, what are the changes that I observe for a given level of global warming? So in these specific cases, we would take the two periods that correspond to a global warming level of 2 degrees and basically use the simulations to look at future changes. And what you get is what's shown on the next slide. And in this study, they go an extra step. And instead of using runoff or flow simulated by the GCMs, they take the GCM output, so precipitation, temperature, and they use it to force several hydrological models. And what they do is that they produce maps of future changes for different global warming levels, so 1.5, 2 degrees, and 3 degrees Celsius. And you can see, we can recognize actually the patterns that I discussed at the very beginning of my presentation, with this gradient with northwestern Europe showing larger flood peaks, and most of the rest of Europe, including Scandinavia, showing smaller flood peaks. The bottom panel is also interesting. When you see yellow, it means that the contribution of the hydrological model to the uncertainty is as large as the contribution of the climate models. So it really shows the importance of using more than one hydrological model. Next slide, please. And once we have actually the simulations, one option is to adopt a dynamical approach and to use flow simulated by hydrological models, and to combine the flow simulation with channel bathymetry, some terrain data, for instance, LiDAR data, and use all this information in a hydraulic model like LISFloodSP, which is what we use at Fathom. So this is a dynamical approach. It's quite expensive computationally. So at Fathom, we developed a different approach, which is based on change factor that my colleague Nat will tell you about. So I'll hand over to her.
Thanks, Nans. Yeah, so we've covered some of the theory about how floods might change in the future in response to changes in climate, and also some of the ways that this can be modelled. So I'm now going to focus in on some specific examples to show how we at Fathom have gone about modelling changes in future flooding on different spatial scales. Firstly, we'll have a look at Fathom's climate dynamics. So this is our framework for modelling future changes in climate, future changes in flooding, for pluvial, fluvial and coastal flooding for any future scenario anywhere in the world. And I'll just be giving a really brief overview of our climate dynamics framework. So if you'd like more information, please have a watch of our climate dynamics launch webinar, which is available from our website. Next slide, please. So in the first Cyber webinar that we gave in November, we talked about some of the methods that can be used to link data from global climate models to flood models, and Nans has also touched on them. And one of the methods that we talked about were change factors. So this involves using the relative changes that we calculate from climate models to update our historical baseline data for our pluvial, fluvial and coastal perils. So this historical baseline data is based on observations of precipitation, river flow and coastal water levels. And by using this approach, it allows us to link the output from the relatively coarse global climate models to our high resolution flood maps. So we calculate change factors for different levels of global warming, as Nans has referred to earlier. And this gives us kind of full flexibility in which emission scenarios and future time periods we can produce first hazard data for, because we map any scenarios that we might be interested in or time periods to the level of global warming that has occurred for that scenario, and then produce our future flood data based on that warming level. So as a simple example, if we just look at the plot on the right-hand side of the slide, we can follow the red arrow vertically upwards to see that a global warming level of 2.5 degrees C results in a change factor of 1.5. And this is equivalent to a 50% increase in the variable we're interested in, which might be extreme precipitation, for example. And we calculate probabilistic change factors for each peril from ensembles of models, where we can, so that's ensembles of climate models or hydrological models or coastal sea level models, rather than single models, because this allows us to estimate the uncertainty and the confidence associated with our projections. Next slide, please. So we'll now have a look at some examples of change factors that we use for different perils. So first we'll look at the pluvial change factors. As Nans has mentioned, the Clausius-Clapeyron equation tells us that extreme precipitation is likely to increase as the climate warms in the future. But rather than assuming that extreme rainfall increases everywhere at the same rate, we instead use an ensemble of 4 bias-corrected global climate models from the CMIP6 high-res MIP project to try and capture some of the spatial differences in the changes in extreme rainfall that we might expect in the future. So on this map, the background colour represents the multimodal median of the change factors for extreme precipitation for a global warming level of 2 degrees C. And the hatching on the plot shows areas with low model agreement on the sign of change. So if fewer than 3 of the 4 models project the same sign of change in precipitation, so either an increase or a decrease, then we have lower confidence in the climate projections in that region because the models can't agree. And as you might expect, based on the Clausius-Clapeyron equation, extreme precipitation increases in most regions, and the average globally is approximately similar to Clausius-Clapeyron, but you can see from the map that there is actually a fair amount of spatial variability. And you can also see that only a limited numbers of areas are hatched, which indicated low confidence. So for this ensemble of models that we've used, this shows that they generally agree on the sign of change in precipitation over most land regions. Next slide, please. So this is an example of our fluvial change factors, which were produced using an ensemble of 2 global hydrological models, which were each forced by 4 bias-corrected global climate models as part of the CMIP5 ISIMIP2B project. And once again, the background colour represents the multimodal median of the change factors, but this time they're change factors for river flow, but again for a global warming level of 2 degrees C. And the hatching again shows areas with low model agreement on the sign of change, so where fewer than 3/4 of the model project the same sign of change in river flow. And whilst we saw on the previous slide that extreme precipitation is projected to increase in most regions, the picture is not so simple for projected flooding, and Nans has already talked about this using some of those papers that he presented. So on this plot, you can see that the regions in green show an increase in flood peaks, but that actually many regions are highlighted in brown. And this shows that they're expected to have smaller flood peaks in the future at 2 degree warming level. And this is related to changes in different flood drivers in these regions, including soil moisture and changes in the snowpack. You can also see from this plot that there are larger areas of hatching, which shows that there's more uncertainty in the projected changes of flow, with lower confidence in the sign of change across the models than we saw for the pluvial change factors. Next slide, please. Finally, we've got the coastal change factors that we use in our global flood maps. These are based on the IPCC AR6 regional sea level projections, which are based on a synthesis of a series of different models and emulators, which are used to individually simulate the different drivers of sea level rise, such as melting of ice sheets and thermal expansion of seawater. And this map shows the median absolute change in sea level for SSP 24.5 in 2050. So this is approximately a 2 degree warming level. And we can see that increased sea levels are projected almost everywhere, which you might expect, with some regions, such as around the Gulf of Mexico, showing particularly large increases, which is related to oil and gas extraction and land subsidence in these regions. There are also some limited areas which expect a decrease in sea level in high northern latitudes, and this is related to changes in past and present day ice sheets. Next slide, please. So in order to produce our global flood maps, each of these sets of change factors is used to update our historical baseline data. And this allows us to produce inland and coastal climate condition flood hazard maps, such as the one you see on the right-hand side of the slide, which shows the increased depth and extent of fluvial flooding for a 20-year event under a warmer climate compared to a 20-year event under a current climate. And by using the approach of defining our change factors in terms of global warming levels, it means that we can produce flood data for a flexible range of future time periods, warming levels, and emission scenarios. Next slide, please. We've talked about global scale flood modelling, but what if we're interested in future changes in flooding over a smaller region? It might be now that global climate models aren't the most appropriate tool to use because coverage and physical consistency on a global scale may now be less important to us. Next slide, please. So Nons has mentioned already that climate models are really highly complex. They represent many parts of the Earth and climate system. And as a result of this complexity, and particularly when they're run on a global scale, they require a huge amount of computing power and time, which means that they're often run at relatively low spatial and temporal resolutions, and particularly when we're comparing to the kinds of resolutions that are required for risk modelling. So if we're interested in a smaller region, then climate data from regional climate models, which Nons has mentioned previously, are available and are likely to be more appropriate to use. The regional climate models are still driven by data from global climate models, but they can be run at a much higher spatial and temporal resolution due to the smaller domain that they're covering. And this means that things like topography and its influence on precipitation and flood processes is better resolved compared to in global climate models, as we can see in the figures on the right-hand side. So if we look at the top panel, we can see the resolution of a typical global climate model, which has grid boxes that are approximately 150 by 150 kilometers in size. And because the topography is averaged across the area of each grid box, there's not much variation between the different grid boxes. Below that, on the middle row, you can see the topography of a typical regional climate model with grid boxes of around 25 kilometers. And you can see more spatial detail starting to be resolved now at this resolution. And at the bottom is the 30-meter resolution of our flood hazard maps, which captures much more spatial detail and smaller scale features. Other processes which are also important for extreme rainfall in many regions, such as convection, are also parameterized in global climate models rather than being physically represented, as this requires spatial resolutions of a few kilometers. These very high resolutions of a few kilometers aren't currently practical on a global scale, but on a regional scale, these processes are starting to be physically represented in models now, and I'll touch on this more in a few minutes. Next slide, please. So one example of a set of regional climate models is from the CORDEX project, which is an international program that aimed to better understand relevant regional and local climate phenomena and their variability, and also how they might change in the future through downscaling of climate data. And they used a range of different regional downscaling models and techniques, which they also evaluated. And these include dynamical downscaling using regional climate models, which were forced by global climate models, and then also direct statistical downscaling of global climate model data. And the current resolution of the downscale data is around 25 kilometers, and you can see the different model domains that they cover on the left-hand map, and then a close-up of the European domain on the right-hand map. Next slide, please. The UK Met Office's 2018 UK climate projections, also known as UK CP18, are another set of regional climate model projections, which were run for a range of different emission scenarios, covering the UK and sometimes Europe, at a range of different horizontal resolutions. A set known as the regional projections, which have a horizontal resolution of 12 kilometers, we used in this paper in order to explore uncertainties in the impacts of climate changes on high flows across Great Britain. So they use an ensemble of 12 regional climate model simulations with perturbed physics, which essentially means that the physical parameters in the models are varied in order to assess climate model uncertainty. So just varied by a little amount to see how sensitive the climate model is to those different parameters. The bias corrected data were then used directly as input to the Decipher hydrological modelling framework across around 300 catchments in order to produce flow projections for a historical baseline period of 1985 to 2010, and then a future period of 2050 to 2075. And in the figures, we can see the projected change in annual maximum flow for 3 of the regional climate model, hydrological model ensemble members, selected because they show the highest, median and lowest Great Britain averaged change in flow. And you can kind of see quite an evident north-west southeast divide in the flow, with northerly and western regions generally seeing increasing flood peaks, while southern and eastern regions tend to see a decrease, particularly in the southeast England, sorry. And this drying in some of the southern regions is related to increased evaporation and the drier antecedent conditions, which then lead to smaller flood peaks in the future. The paper also looks at a number of different indicators of peak flow, so how you define peak flow, but they generally showed similar spatial patterns, but with quite different magnitudes of change. And so this paper and figure quite nicely illustrates some of the uncertainties involved in modelling future flow flood changes. So in this example, only parameter uncertainty in the climate and hydrological models are considered, and which indicator for peak flow is used, and yet there are still some quite significant differences spatially and also in the magnitude of change. Next slide, please. So another example of climate-adjusted flood modelling on a regional scale is Fathom's UK flood map. Next slide, please. So for this, the UK CP18 regional climate model projections were again used, but here a change factor approach was used, similar to the one that we applied and talked about in our global climate model, in our global flood model. The UK CP18 climate data was used to calculate pluvial and fluvial change factors, which are shown on the left and central maps for year 2070 and the high emissions scenario RCP 8.5. And you can see on the left-hand plot that pluvial change factors are positive in most areas, indicating increasing extreme rainfall, although in some areas, particularly along the northeastern coasts of England and Scotland, you can see a slight decrease or little change in rainfall. And spatial patterns in the fluvial change factors show more differences, as we might have come to expect by now, with larger areas of drying projected along the east coast. And again, this is likely related to different drivers of floods as mentioned previously. And interestingly, this kind of east-west or north-south divide that we've seen in the changes across the UK over the last few slides aren't seen in our global change factor data, which is derived from global climate models, which really just highlights that the projected future changes that you might see for a region can depend very much on the input climate data that you're using. So it's really important to use the kind of most appropriate and best climate data set for your particular application. If we look at the right-hand plot, we can see the coastal climate change simulation change factors, which were calculated using sea level rise changes published by Kopp et al. And as you can see, and you might expect, sea level rises everywhere, but by different degrees, with larger increases along the southeast coast of England and then smaller increases along the northwest coast of Scotland, which is a result of isostatic adjustment of the land in this area following the ending of the last ice age. Next slide, please. So one of the key uses of future flood hazard data is to assess changes in losses due to flooding. And you can see from the map on the bottom right-hand side that changes in expected annual damage in the UK due to warming of a 1.8 degrees C show significant spatial variation. And you can see in the patterns some evidence of the footprints from the different flood perils, which are shown in the top panel of plots, but you can also see some differences. And this is due to the complex interplay between changing flood drivers as well as changes in future exposure of assets. Areas showing significant increases of more than 25% compared to historical conditions are seen over southeastern England, southwest Wales and northwest England, while more modest increases occur over much of central and western Scotland. And meanwhile, small decreases in flood losses occur over southwest and central and northeast England. And results such as these have really important implications for both future climate action, but also flood adaptation in the UK. Next slide, please. And finally, we'll look at an example of a more localised flood modelling study. And this is provided by a research project that Fathom was involved in collaboration with the UK Met Office and the University of Bristol. Next slide, please. So for this, a convective permitting model developed by the Met Office was used, which was known as UKCP Local, which has a resolution of 2.2 kilometres. And so due to this really high resolution, the model was able to resolve much smaller scale spatial temporal rainfall features and processes, such as intense convective storms. And this is evident from the maps on the right, which compare hourly rainfall for the same flood event from 1998. So you can see that between the two maps, the large-scale features are very similar between the 12-kilometre and the 2.2-kilometre data. But in the 2.2-kilometre model on the right, you can see more local showers are captured, which are kind of highlighted by the top right arrow on the plot. And the high resolution also provides a more realistic representation of rainfall, including areas of high intensities that aren't seen in the 12-kilometre data, but are highlighted by the bottom arrow on the right-hand plot. So in this study, events were extracted from the climate data and were routed directly through ListFlood FP 2D hydraulic model over the Bath and Bristol area in order to produce flood inundation. And for comparison, inundation was also produced by applying climate uplifts, in other words, change factors, derives from the UKCP local data to historical IDF data for precipitation. And it was found that the use of an event set from a convective permitting model results in greater inundation. Oh, next slide, please. Results in greater inundation compared to that produced by applying change factors. This is illustrated in the plot on the right, where the yellow two red bars represent inundation produced using the event set approach for 3 different time periods, and the greens and blues represent the change factor approach for those same time periods. And you can see that for each of the time periods, the yellow, orange, or red event set bar is higher than their equivalent light green, teal, or blue uplift bar, indicating a larger flooded area. And this difference is because more spatial temporal features of rainfall, such as convection, are explicitly captured by convective permitting models, often resulting in higher rainfall intensities. And as climate models and supercomputing capacity develop in the future, it's likely that there'll be a move towards developing these very high resolution models over larger areas, and hopefully one day globally, which will have really large implications for flood and risk modelling in the future. So this is a very brief overview of some of the ways in which the impacts of climate change can be accounted for in global to local scale flood modelling. So I'll now hand back over to Gavin to discuss how large scale flood modelling data can be used in industry.
Great, thank you, Nat, and thanks for that information. I think that I've learned some new things there as well today, which is really important. What I'd like to do is really talk about putting the science into context with some real world examples. But before I do that, I really think it's appropriate to look at where this type of data can really influence and be used within the typical engineering type project. And workflow. So the type of data that we're using really sits at that front end of projects where you need to understand the initial impacts or the scope or the size of projects, where you're looking at things like feasibility analysis, looking at preliminary screening of assets to select particular assets for investment, or looking at adaptation processes. So by using this data, it really gives a much wider context and evidence for that swifter, more informed decision making to help shape those strategic business cases, perhaps, or investment cases for projects to then flow through to the more detailed design that engineers typically do, to then focus the resources and the time more appropriately on the areas that actually need investigation in more detail. That have been highlighted through this type of large-scale, high-resolution flood and climate data. But by doing so, it can help make those decisions more appropriate, provide a good evidence base, but also then inform the downward flow, particularly when you're sharing that information with your clients going forward. So one of the areas we can look at is site assessment, and that could be selection of sites for acquisition or placement of certain assets. It could be investment, but it's really, there's 2 scenarios here where you're looking at high-level screening of a portfolio of assets, where you need to know, actually, are these assets going to be impacted by flooding either today or under future climate scenarios? And you could rapidly screen those assets using flood scores, flood risk scores that are based on the flood maps. And on that, you can really triage those assets and say, okay, I've identified out of my portfolio which are the key assets that I need to do a much more detailed analysis. So that's when you use those flood and climate hazard maps to give a much more in-depth review of each site, using the 3 sub-perils but also using that defended and undefended views for both the fluvial and the coastal flooding. So you can get a much better understanding of the impact of flooding on your sites, both today and under any future climate scenario up to 2100. But essentially, as this data set is global, you get that consistency. So when you're looking at assets, it could be at a regional, at a country, or a global scale, then you're comparing and getting that consistent review of data, which is important when you're making investment or decisions around resilience and adaptation. So a good example here is solar farm. This is an example of some of our data has been used by one of our clients that acquired a series of solar farms in the US, and they applied our data to do some due diligence and identified this particular site that was impacted by flooding, that they'd had some site records to identify there were problems on the site, but they were able to identify what those problems were and actually quantify them. So rather than write the site off, they were actually able to use the data to rearrange the solar array and make it this site much more viable. So it's using this detailed level of climate condition flood models for this type of site assessment can very quickly bring around benefits and identify problem areas to then start getting into that much more detailed analysis and looking at the flexibility and development of selection of sites. Now, that's just individual sites. When we're looking at linear assets, we've got we're living in a world now where the extreme flood events have recently become sort of more business as usual under changing climate. So there's a critical need to really enhance the asset resilience to accommodate the impacts of climate change, to raise the threshold of what we believe to be acceptable risk. So by embedding future flooding consideration into the business planning and asset management processes, we can increase the resilience by railways, highways, and other assets that are distributed over very large areas, whether here in the UK, whether in the US, or actually globally. But that's not just for the development and building of new assets. Of course, it's looking at the service delivery, maintenance of the existing infrastructure that is all around us. So these climate condition hazard maps can really provide a very quick way to screen linear assets and rapidly identify what we think to be the wet spots to provide a higher resolution, more definitive understanding of current and future climate risks across any network. And really, you're looking at that delta between best case and worst case scenarios to help inform the decisions for resilience investment, prioritization, and ultimately adaptation. So this is a good example where we worked with Arup on this project in Dar es Salaam, Tanzania. So the city is a very low-lying coastal city with a population of over 7 million, which is set to double by 2050. And so the project was really set up by the World Bank to address the challenges of rapid, unplanned urbanization, together with the combined impacts of climate change on flooding, erosion and sedimentation, water availability, and the urban heat island effect. So using our automated modeling framework, we were able to apply the current and future urbanization projections of the city that Arup developed. And we overlaid those and built them into our flood modeling automated framework to provide a current and future views of flooding and the combination of urbanization. So we provided that combined perspective and identified the areas that are going to be impacted and where there was increased flood risk. Arup then took this data, this combined model, as a key input to develop a range of nature-based solutions or the options for nature-based solutions to mitigate the increased flood risk across the city. Once they developed these various options, we then applied them to the combined model in our automated modeling framework to then identify the locations benefiting most from these particular nature-based solutions, as can be seen here in this image. And this is across the whole city, and it really identifies those areas that could potentially benefit from these NBS interventions. So through this swift modelling of future climate and urbanisation impacts, it really enabled Arup to rapidly develop the most appropriate options for the nature-based solutions, and to derive a number of benefits. For example, 17,000 buildings were less susceptible to flooding. That was developing an area of about 12 kilometres squared of urban area that were no longer flooded. They were looking at the absorption of about 300 Olympic swimming pools of rainfall in the soil, reducing the heat island effect by between 1 and 5 degrees C, and reducing the average soil loss to help preserve riparian areas. So this is where our data, we can work with partners to take our data, integrate it into their applications, and actually provide real world answers to some of these issues around climate change and flooding. So before we go into our question and answer session, we'd like to have our second poll on use cases of flood risk and climate risk data. So I'd like you to please answer the questions that come up on the poll. And whilst you're going through that, hopefully the poll is going to pop up soon. And whilst you're answering the poll, I'd like to remind you that we will be sending out a link to this webinar in an email to you tomorrow. So if you've missed some of it, then you can quite easily click on the link and download the recording. And also, if you're any of your friends or colleagues that are interested in flooding and climate change, it'd be really good to share the link with them so they can look at this and perhaps also gain their CPD points. Okay, thank you. There's some good answers there. Interesting. Again, we're going to be sharing these results with you and give you a bit of a flavour of the respondents that we've received, because I think it's quite important. We're getting a lot of input here as to those types of areas where you believe this type of data could be applicable. Okay, great. Thank you very much. Let's end the poll there. So what I'd like to do now is if we go to the is look at a number of links that we will share with you on the around the future events that we're doing. The next CIWEM event is exploring the impact of compound events. That's on the 20th of August. Before that, we've got another webinar at the end of this month where we're talking about our global flood mapping and putting it into more detail and more context for engineers for understanding and modelling flood risk and climate change. So let's turn to the questions. And if my fellow attendees, speakers can join us, we'll go through the questions here. So the first question I believe we've got here is from John. How was the GCM-HM uncertainty Russian calculated?
Yeah, that's a great question. So the method used here typically is an analysis of variance, so ANOVA. So in the Tauber et al. Study I showed, they have 5 GCMs for things, 3 HedgeCloud models. So they combine them all and gives them 15 members. And so the spread of these 15 members basically can be attributed to the variance, and the variance can be decomposed. So you can ask, oh, how much of the variance can be attributed to climate models? How much can be attributed to HedgeCloud models? And if you say we have, for instance, 40% explained by the global HedgeCloud model and 40 by the GCMs, then that's the regions that appeared in yellow on the maps I've shown. So basically, anisovariance is how the uncertainty is decomposed.
Okay, thanks, Nance. We've also got another question from John. How is the change factors, e.g. from heavy precipitation due to 2-degree warming, propagated into the flood map generation? Is the hydrograph scaled? Are antecedent conditions derived stochastically? Or are the future time periods runs simulated as a continuous run as opposed to event by event?
So it's the latter. It's all based on continuous simulations. So we use hydrological models that were run over the entire 21st century, simulating soil moisture over the 21st century. And the soil moisture has an influence on the shape of the hydrograph, and our change factor capture these changes. And then we propagate these changes into our flood maps.
Thank you, Nans. Right, next question. We've got Thomas. What global reference data sets has been used for bias adjustment for the GCMs and for which parameters? Nans.
Yeah, so for all the projection we used, bias correction has been done. For bias correction, we need a global data set, as you mentioned. And for this, we use reanalysis. And these reanalyses are great because they're global and they're also pretty high resolution, but they have some biases themselves. So we use climatology to bias correct ERA 5 for the pluvial change factor and ERA interim for the fluvial change factor. And the fluvial change factor part, I mean, the data for the fluvial change factor was produced by the EasyMIP project. So yeah, reanalysis data, bias corrected is the answer.
Thank you, Nans. Another question from Thomas. Could you comment on the yet poorly representative convective rainfall by GCMs and to which degree this affects the quality of flash flood simulated by Fathom's hydrological model? Nat?
Yeah, that's a good question. I think I touched on it a little bit, but it's difficult because, as I mentioned, climate models that are run over the kind of resolution that you need for convective processes are only run over very small domains at the minute, just because of the high levels of computing and time resource that are needed to do those simulations and the huge amount of data that is produced from them. If we're looking at a global scale, it's important that we use globally consistent climate model data, which is why we kind of choose to use global climate models, but obviously they do potentially underestimate extreme rainfall from convective processes. We've tried somewhat to mitigate the resolution issue by selecting a high resolution ensemble of climate models rather than kind of larger ensemble of lower resolution CMIP6 models. We use high-res MIP, the high-res MIP ensemble, which is the kind of quite a state-of-the-art set of climate models that are the first set of global climate models run at a regional climate model resolution. So they've got a grid box resolution of around 25 kilometers, and they're kind of deliberately designed to provide a more reliable source for assessing climate risks that are associated with small-scale weather phenomena. But as the Archer et al. Paper showed, not physically representing convective processes can result in underestimates and extreme rainfall. So as higher resolution data hopefully increasingly becomes available in the future, we'll be able to kind of use better climate projections on smaller scales to incorporate into our flood modelling. And it's likely that our future projections of flooding may change just as that kind of better quality data becomes available publicly. Thank you.
Thank you, Nat. We've got time for a couple of quick questions before we wrap up. One from Ishmael. Are the GCMs available to the public? If not, how can they be accessed? Can they be used with local parameters? Nat, I think that's probably one for you.
Thank you. Yeah, so it kind of somewhat depends on which GCMs and which ensemble you're interested in. The Met Office, UK Met Office data sets are generally used. A lot of the GCMs are available. If you go to the CMIP6 website, they're available for download. They do include quite a lot of large amounts of data depending on what resolution and what how many variables you're interested in. It's not possible to use local data because it's not the models themselves that are available, because they're run on kind of supercomputers at various universities and institutes around the world, but it's kind of sets of climate model data, so things like precipitation and surface air temperature and sea surface temperature and things that have already been produced for a kind of defined set of simulations, so for specific emission scenarios and specific time periods, and they're what you can download. But yeah, if you go to the UK Met Office or the CMIP6 websites, it should have more information there about how to access that data.
Thank you, Nat. Last question, we can just squeeze this in. It's probably not a straightforward answer, but one for you, Nans, from Rowan. How would you explain the differences between your predictions for Southeast England has a reduction in pluvial flood peaks versus the Environment Agency predicted peak river flow allowances, which broadly show small increases.
Yeah, so that's a very good point. I touched upon the fact that projection of future changes in flood peaks are quite uncertain, and they depend on the model that is used. And so if you use different models, you might get slightly different answers, and the model that the A used is different from the model that, I guess you're referring to the Natal paper that Nat showed. So if you use different models, you get different answers. In the case of East Anglia, it's really interesting because the projection, UKCP 18 projection there show a very strong drying over East Anglia that is stronger than in the rest of the country. And this is consistent with a decrease in flood peak that Nat showed. The Natal paper is in open access, and they include a really interesting analysis showing how less soil moisture, so drying of the land, can be used to explain a smaller flood peak in Eastern England. So yeah, I suggest you check out the paper. It's a very interesting piece of work. But again, I mean, there are uncertainties there, and so it depends on the model that we're using. Ideally, we would use all the models and produce a large ensemble, and this would actually represent more uncertainty a bit better than using a single model. Thanks.
Right. Thanks, Nans. Well, thank you everyone for joining us today. We've got some links in the chat panels to the first SciWAMP CPD webinar we did, and also to book up for the next one we're doing later in the year. There's also a link there if you want to find out more about any of the data or the science we've talked about, to click on that link and set up a call with myself or one of my colleagues to get into the detail. But thanks very much for joining us, and thank you for all those that provided some really interesting questions. The link for this webinar, as I said, was going out will be out tomorrow. But I'd just like to thank Natalie and Nans for their contribution today. And I'd like to thank you all for joining, and we look forward to seeing you on the next webinar in a couple of months' time. Thank you very much. Have a good day.